recording, and then here we go. It is my absolute pleasure to introduce to you Rupak Majumdar. He is a tenured faculty as well as a scientific director at the Max Planck Institute for Software Systems in Germany, and he is interested in algorithmic techniques for verification and testing in general. He was also, just in the context of POPL, he was the program chair or the general chair. Let me just double check my notes for POPL 2016. There you go. Rupak, please take it away.
Thank you, Azelia. Thank you for the introduction and also for inviting me. So it's good that I'm talking right after Ichiro, because in some sense, he kind of introduced many of the topics that that will also show up in what I talk about. But my hope is that I can keep the talk at a somewhat more informal level, and we don't get into a lot of technical details. I mean, there will be technical details, but I hope that you would not need a lot of background in following what's going on. Okay. So essentially, in programming languages research, one of the core things that we do is that we model systems that evolve over time, and then we try to reason about the behaviors of these systems. So here's a very canonical example. It's called the reachability problem. So what you do is you model the system somehow as consisting of states and transitions between states. And a lot of different things, hardware, software, and so on. You can model roughly, in this way of, you have states and you have transitions. And over time, the state goes from one, the system evolves from one state to the next following the transitions. And the reachability problem is a very basic question, right? It says, suppose I give you this kind of a model. I give you some initial states and some bad states. Is there a way for the system to go from some initial state to some bad state? And in some sense, this is really at the core of safety verification, a lot of type systems, and so on. And if you model the system using discrete states and you think of the transitions happening in discrete time, not necessarily real time, but logical time, then reachability reduces to graph search. Of course, this graph can be very large, or it can even be infinite or unbounded. And in general, we will not have an algorithm that will solve the reachability problem in all cases. For example, you can think of the states as Turing machine configurations and the edges as Turing machine steps. But a goal that we always have is to find interesting instances where this problem is decided. Now, one way to tackle this problem is through what is called axiomatic reasoning, which is essentially a way to encode the problem in a suitable logic. So instead of looking at one state at a time in this large graph, you pick some logic and you represent sets of states using logical formulas. And then you manipulate these sets of states by manipulating formulas. Right? So the syntax of these formulas gives you a representation for sets of states. And manipulations of this formula allows you to manipulate sets of states of the system. And similarly, you can represent the transition relation as a logical formula. And then you can derive functions that tell you what happens if you're in a certain state and you take one step. Right? So, in model checking, these would be called pre or post. In program verification, these would be the weakest preconditions or strongest post conditions, and so on. But essentially what we do is that by doing this kind of encoding, we reduce reasoning about the system to checking validity of logical formulas. And at this point, you look for decision procedures for particular logics. And then, if you have such decision procedures, you can answer questions about these systems. So if you have heard of SMT solvers, essentially these SMT solvers allow you to use these kinds of logical encodings. And then they have built-in decision procedures for certain logics that allow you to answer these validity questions. Right. So this is more or less, a very classical problem in programming languages. You will see a lot of instances of this reachability problem and logical encodings in the next few days. But let me ask the following question. So what can we do if our systems are not these kinds of discrete state, discrete time, but these are given by ordinary differential equations that evolve in continuous time. So just going back to your engineering education, these ordinary differential equations tell you how the derivative of a differentiable function evolves over time. So here, for example, I'm saying x dot, the derivative of x with respect to time satisfies, is equal to some function of x, right? So you have some state and the derivative tells you how the state evolves over time. And a behavior of such a system is a trajectory in continuous time that satisfies the differential equation. Now, the reason we study these kinds of differential equations is that a lot of systems that are called cyber-physical systems that, of course, Ichiro talked about an hour ago, essentially have this flavor, right? So these are systems where physical processes are controlled by software. And the physical processes are usually modeled by these kinds of ODEs, and the software is modeled by programming languages. And what we'd like to do is to reason about the combination of ODEs and programming languages. And let's go back to the simplest question that we can ask about those systems, right? Suppose I give you one of the simplest possible ordinary differential equations. These are called linear equations. Essentially, you have x dot is some matrix A multiplied by x. Okay, so it's essentially the derivative is a linear transform of the state. And again, I give you a set of initial states. I give you a set of bad states. And in addition, I also give you a time bound, capital T. And then I ask you, is there a trajectory from some initial state to some bad state that goes to the bad state within the time bound T? So in some sense, this is the simplest analog to the reachability question that we have seen before, right? So again, we have a system given by an ODE. I have initial states, I have bad states, and I even have a time bound. And I want to see if you can reach one of the bad states within this time bound. Quite surprisingly, we do not know if this simple problem is decidable. Of course, we can numerically solve this equation and we can compute to any accuracy, but it still doesn't allow us to answer this question in all possible instances. Because essentially, no matter what precision you choose, there is always some uncertainty whether you actually reach a set or whether you're really close to this set. And it turns out, there is this problem has a very rich pedigree. In the discrete time case, it's called the Skolem problem. In the continuous case, it's the bounded Skolem problem, as these gentlemen have published about 10 years ago. Now we can take the logical view, and one thing you remember is that, well, for linear dynamical systems, for linear ODEs, I can actually write down an analytic solution. I can write down, where x is at time t as an explicit function, which involves something called the matrix exponential, but roughly, in terms of multiplications, exponentials, and trigonometric functions. And again, I can write down this logical formula that essentially says what we wanted to encode in the problem, where you start at x0 in some initial position. You want the x of t to be in some bad state. And this t should be, well, it should be greater than or equal to 0 and less than or equal to the time bound capital T. And x at time t is given by this function that involves exponentials, trigonometric functions, and so on. And in fact, this problem is unknown even if x0 is a single point. And so the initial state set is a single point with rational coordinates. And the bad set is given by a hyperplane, right? Or let us say in general by some polytope. Okay. So assume these are polytopes. What kind of reasoning do we need to do? So in some sense, if you want to be able to solve or check if formulas like this are satisfiable, we need to look at what in the business we would call the theory of real arithmetic, with addition operations, multiplication operations, exponential functions, and trigonometric functions. And the question is, if you have a logic which has all of these features, you can add numbers, you can multiply them, you can take the exponential of a number, or you can take the sine or the cosine of numbers. Can you reason about them? Is this decidable? Well, we already know that this problem is actually not decidable because, if you have addition and multiplication and you also have trigonometric functions, you can define the natural numbers. And there is a very famous result by Gödel that says, well, if you have the theory of natural numbers with addition and multiplication, then this is undecidable. Of course, because the theory is undecidable does not mean that this particular problem will also be undecidable, but perhaps we can restrict the logic in a certain way. And here's a way we can restrict the logic, right? We know that we have this upper bound capital T. So in some sense, we are not interested in whether such formulas are satisfied over unbounded domains. We could ask, suppose that I restrict the domain of all of these functions to some, so let's say 0 to 1 without loss of generality. Is the theory then decidable? And again, this is something that we don't know at this point. But we do know quite a lot about related theories. For example, the theory of linear arithmetic, where you can only write linear relationships between variables, is this is known to be decidable, and every SMT solver that you can find will have an implementation of linear arithmetic. In some sense, if you can use procedures for linear programming to solve this problem. And linear arithmetic allows you to write, polytopes, but it doesn't allow you to do multiplication or have these other functions. It is also known, and this is a very famous result by Tarski going back to the 40s, that if you have the theory of reals and you're allowed to do addition and multiplication, then the resulting theory is also decidable. So there is an algorithm that will take any formula and tell you whether this formula is satisfiable or not. And in fact, Tarski's paper left open this decidability of the theory of reals if you add the exponential function. Okay? And the paper also showed that if you also add trigonometric functions, then it becomes undecidable. All right. So we will come back to this logical view. So the goal of this talk is to essentially think about what needs to be done in order to check if this theory is decidable. And I'll give you the punchline up front, right? So we don't know if this theory is decidable, but we can show that this theory is decidable if there's some relations among complex numbers hold. So here's the plan for the rest of the talk. So I'm going to go through a journey where we shall look at numbers, starting really very far back in the past. And I will show you, some very interesting steps in the progress of our understanding of numbers. And at the end, we shall get to a point where we shall be able to at least state the result that this particular theory is decidable, assuming certain conditions hold on the numbers. So because this is more of an expositionary talk, I'm not going to be very careful about giving all the detailed citations and all the for all the results. But if you're interested, just talk to me offline and I can tell you where to look more. All right. So essentially our journey, our quest, as it were, starts a long time ago. And really, in the prehistory, humans already knew how to count, right? So there were numbers and we would use these as counting numbers. We would say, okay, we have 3 apples and then maybe somebody else has 5 oranges and so on. And one of the very early advances in mathematics is the understanding of the number 0 as its own number. Now, of course, very early on, people understood positional number systems, and in some sense, 0 was used as an absence of a number. But one of the early advances in our understanding of numbers was the understanding that 0 by itself is a number. Once you have this view, you can start thinking about the structure of the numbers. You can think of it as an additive group and so on. And so, the introduction of 0 was really one of the watershed moments in our understanding of numbers. So incidentally, I think, the history is not quite clear, but I think the Indian mathematicians back in the 4th century AD started thinking of 0 as a number of its own. And this very quickly spread to the Persians and the Arabic mathematicians. And in fact, it came to Europe, and there was a very influential book written by someone called Leonardo from Pisa. And you might know him better as Fibonacci. So, essentially people generally realize that 0 is a good thing. And of course, the other kind of numbers that you had after you had the counting numbers are the rational numbers. So these are ratios of two natural numbers. And again, the ancient Greeks were very familiar with rational numbers. And in their geometric view of mathematics, these were essentially proportions that you could geometrically construct. Given two lines, you could construct a line that is whose length is essentially the ratio of the lengths of these two lines. And one thing you probably know about rational numbers is that there are exactly as many of them as natural numbers, right? So there are, both of them, there's an infinite number of natural numbers, an infinite number of rational numbers, but you can find a bijection that maps every natural number to a rational number and back. But of course, rational numbers are not the end of the world. There are more numbers. And very quickly, the Greeks kind of figured this out. And this comes already from Pythagoras' theorem, right? So Pythagoras' theorem, if you recall, says that if you have a right triangle with sides A, B, and C, then A squared plus B squared is equal to C squared. Now, if you take A and B both to be equal to 1, then you know that C is the square root of 2. And very early on, Pythagoreans realized that square root of 2 is not a rational number. Now, there is this very famous story that Hippasus, one of the people in the Pythagorean school, realized that square root of 2 is not a rational number. But in the worldview of Pythagoreans, the rational numbers were really perfect. God has created the rational numbers, and that's all there is. And so there is this apocryphal story that, when Hippasus showed his proof that square root of 2 is not rational, people got so upset that they essentially killed him by drowning him in the sea. It's not clear if this story is true, but it's essentially one of those early stories of denying tenure to people just because you don't like their research. But yeah, things were more wild back then. Anyway, so what does it mean that the square root of 2 is not rational? Well, it means that if you take any two numbers A and B, which are natural numbers, you cannot write square root of 2 as the ratio of these two numbers. So how can we show this? So let us try to prove that this is indeed not rational. And there's a very cute geometric proof that I'm told was found by Stanley Tenenbaum, but perhaps this was already known to the Greeks a long time ago. So it says the following, right? So in order to show that A by B is not equal to square root of 2, I can equivalently say that A squared is not equal to 2B squared for any AB. And so Tenenbaum says, okay, think of the smallest instance of a square A that can be written as twice B squared, right? Suppose this thing is not true, that you can write square root of 2 as the ratio of A and B. Let's look at the smallest instance A where this happens. Now, what I can do is I can move these squares so that they fit into this larger square. And now what happens is that, look, I have these two little blue squares left on the corners, and their sum must be this orange square in the middle, because those two things are not covered and part of the square is covered twice. So the part that is uncovered must be exactly the same as the part that is not covered, that is covered twice. But now I have found a smaller instance of the problem. And so it must be a contradiction, because I started by saying A is the smallest instance where you can write that as the square of two equal squares. And this is a contradiction, and this shows that square root of 2 is irrational. Now, this is a very beautiful geometric proof. But what about other numbers that we suspect are also irrational? It's not clear that you can get such a geometric proof for all instances. You do get one for square root of 3, and you can think about why this picture could be used in a similar way to show that the square root of 3 is irrational. But it's certainly not so easy to see how you would do such a proof for other irrational numbers. In fact, so Plato had a book where he said that, well, there is this mathematician who showed irrational numbers, so root 3 and root 5 and all the way to root 17. And of course, it's not so clear why that mathematician stopped at root 17, to show that everything was irrational. So one observation is that perhaps they were using these geometric proofs, and these proofs got very difficult after 17. And the other observation could be that they came up against the page limit for the conference. All right. So what we'd like to do is we'd like to see a somewhat different proof. Maybe there is a better proof that that shows that 2 is irrational, that doesn't talk all the way, always about this geometry. And there is a very simple proof that uses essentially the idea of even and odd. So suppose that, again, a by b is equal to the square root of 2, which is equivalent to saying that a squared is twice b squared. What can we say about a? So I know that a is an even number, right? Because you see, if a were odd, then the square root of a would also be odd. And then you would have the left-hand side is odd and the right-hand side is even. And the right-hand side is even because it's 2 times some number. Okay, so let's say that a is an even number, which is twice of a1. Now, if I write this, now I can cancel out the 2. And now I again have a smaller instance that says b squared is equal to twice a1 squared. Now I can apply the same reasoning again, and so on. And then what I get is an infinite descent of smaller and smaller numbers that are all trying to show that a by b, or a n by b, n is the square root of 2. Now, because we cannot have an infinite descent of numbers in the natural numbers, this is not possible. And so we know that this must be a contradiction. Now, a similar argument also works for many other numbers, like the square root of 3, where you try to use divisibility by 3, the cube root of 2, and so on. But certainly not for some other numbers. For example, you will get stuck if you try to prove square root of 6 is an irrational number in this way. Or for example, if you want to show square root of 2 plus square root of 6 is irrational. So let's look at yet another way of showing that the square root of 2 is irrational. And this uses some ideas from polynomials. And what we know is the following, right? So for any number n, the polynomial square root of 2 minus 1 to the n can be written as a number that is some rational number c plus some other number d times the square root of 2. Now, I can always unroll this square root of 2 minus 1 to the n using the binomial theorem. So I can write this as a polynomial. And I also know that whenever I multiply square root of 2 times the square root of 2, I get the number 2. So I can replace recursively all higher powers of the square root of 2 in this polynomial. And then what I would left with is something that has no instance of square root of 2. And that is what I call c. And there's some other part which is a multiple of square root of 2, and let me call that d. So this polynomial I can write down as a rational number c, or in fact, actually an integer c, and an integer d, and then some square root of 2. And now suppose the square root of 2 is a rational number a by b. Then what I know is then c plus d by d times square root of 2 is a rational number whose denominator divides b, because c is some integer, and square root of 2 is a number that looks like a divided by b, and you're multiplying it by some integer d. So whatever number you get, its denominator when written as a rational should divide b. On the other hand, I also know that because square root of 2 minus 1 is a number that's strictly between 0 and 1, if I raise it to the nth power, then as n gets bigger and bigger, this number gets smaller and smaller, it goes to 0. But this is a contradiction, right? Because if you have a rational number whose denominator is at most b, then all of these numbers must be bounded away from 0, right? Because they're at least 1 by b in size. And so again, what we have shown is that the square root of 2 is an irrational number, right? So there you cannot write it as the ratio of two natural numbers. But this last proof actually allows you to show in one shot, or it gives you a proof technique to show many, many different numbers to be rational. And all of these numbers are called real algebraic numbers. So the idea of an algebraic number is that these are numbers that you can get as the roots of polynomials with integer coefficients. So for example, the square root of 2 is an algebraic number because it is a solution of a polynomial equation x squared minus 2 is equal to 0. Similarly, square root of 2 plus square root of 3 is the root of this last polynomial equation, and so on. And essentially in one shot, we have a proof technique now to show that all of these numbers are going to be either integers or irrational. So we have found a way to show that a lot of numbers are irrational. And we could ask, well, is it true that every possible number is a real algebraic integer? So clearly all the rational numbers are algebraic. And so are many of the commonly seen irrational numbers that we have seen. For example, the square root of 2 or the cube root of 2 or the sum of the square root of 2 and square root of 3 and so on. Now, it turns out there are only countably many real algebraic numbers. So countably many, again, means that there are exactly as many real algebraic numbers as natural numbers. And one way of showing this is that, well, look, each algebraic number can be associated with the polynomial that it is the root of. And each polynomial is essentially a finite sequence of rational numbers or integers, and there are countably many of those. So what we have shown is that there are countably many algebraic numbers. But a very famous result by Cantor says that there are uncountably many real numbers, right? So the number of real numbers is really much, much larger than the number of natural numbers. So Cantor's proof that there are uncountably many real numbers does the following. It says, take any enumeration of the real numbers, and then I will go down the diagonal, and I will create a new number that is a real number, but it is not in your list. So it turns out you should not, there is no way of listing out all the real numbers. So here, for example, I'm creating the real number that differs from the first number S1 on the list on the first decimal place, the second number S2 in the second decimal place, and so on. And for those of you who have seen a course in the theory of computation, this picture should be very familiar to you, because this is how we also show that there are languages that are not computable by Turing machines. Indeed, it's the same argument. It's the diagonalization argument, where you take an enumeration of all these languages and then show that there must be a language that's not accepted by any of these. So as an aside, I should mention that Cantor had actually two different proofs of the uncountability. The diagonalization argument actually came later. And his first proof went in a slightly different way. So the first proof essentially said the following, that if you enumerate all the real numbers in any way, and if you pick any interval, then there is a number in this interval that is not in the enumeration. So the way Cantor did this is the following. He said that, okay, look, take all the real numbers and take your enumeration x1, x2, and so on, and fix an interval a comma b. And then what you do is the following. You go down the enumeration until you find two numbers that are within this range a comma b. Take the smaller of those numbers and call it a1, and take the bigger of those numbers and call it b1. And now you continue, right? So you go from this point onwards in the sequence until you find two more numbers that are within this range a1, b1, and you call them a2 and b2, and continue. And now if you keep doing this, then what do you get, right? So eventually either you're going to stop at some finite point and say, oh, look, I cannot find any more numbers within this range that I have at this point. At which point, any of these numbers in this yellow interval are numbers that are not in the enumeration, right? So you have found numbers that are not in this enumeration within this interval a comma b. Or, you take the limits, you can do this process forever, and then you take a limit, and then you have some a infinity, which is the left part, and b infinity, which is the right part of the limit of these intervals. And then every number in the middle is not in the enumeration. And finally, it could be that a infinity is exactly the same as b infinity, and then you can again show that that particular number was not in this enumeration. So essentially, this was Cantor's way of showing that there are uncountably many real numbers, right? This was the first proof. And in fact, what happens if you try to do this with the natural ordering of the rational numbers, right? So let's take all the rational numbers in the interval 1, 2. Then, you can write this as, you order all the fractional parts by the denominator, and then you write down the numerators in increasing sequence. What happens if you do Cantor's argument on this sequence of rational numbers? You actually constructively get a particular real number. And this real number turns out to be, well, drum roll, the square root of 2. So now, this is a different proof from the diagonalization argument that you probably know. And you might want to think about what this proof says about the existence of undecidable languages. All right. So now what we know is that there are many real numbers. And the algebraic numbers are really only a small fraction of these real numbers. And then we shall define these things as transcendental numbers. These are real numbers that are not algebraic. And Cantor's proof essentially says that almost all real numbers are not algebraic, and almost all is in a very precise mathematical sense. It's a set of measure 1. Okay. So in some sense, if I randomly pick a real number, I'm going to get a transcendental number. Okay. So all of the numbers that we see in sort of most real life, the rational numbers or the common irrational numbers, are really only a very small fraction of the real numbers. Most numbers are transcendental. Sorry. But then we have a rather curious dilemma. So we know that there are a lot of transcendental numbers, but for the longest times, we had no idea of proving that a number was actually transcendental. And this is a very curious phenomenon. So assume that you have heard of this thing called an ocean. And you know that the ocean is full of this wonderful substance called water. And then there are these few things like fish and lobsters and whatever. And then someone says, well, can you show me this wonderful thing called water? And you know that if you were to just take your hand and just dip it into the ocean at any point, you're going to get water. But whenever you try to do this, the water kind of slips through your fingers and you come up with a lobster. So essentially, this was a situation in math, right? We knew that there are all these transcendental numbers, but we didn't know how to show that an actual number was transcendental. So one of the first ways of showing numbers to be transcendental turns out to be by someone called Liouville, who essentially showed a result that says that any algebraic number cannot be approximated very well with rationals. And using this observation, Liouville came up with a particular number, which is given here, which is transcendental because Liouville could show that it didn't satisfy this condition that every algebraic number satisfies in terms of being approximated by rational numbers. But certainly this particular number was very unnatural in the sense that, yes, it was constructed explicitly to satisfy these properties of Liouville's approximations, but it certainly didn't show up in normal math. So then the question was that what are numbers that show up in normal math, right? Like e and pi. And these are numbers that we have used in math for a long time. What can we say about these numbers? Now, 50 years after E was introduced by Bernoulli, Euler showed that the number E is irrational. And this was a rather cute and a couple of pages of algebra. And then in the 1760s, Lambert showed using several pages of calculus that pi is irrational. And it was conjectured that it is also transcendental, right? So I mean, everybody thought that E and pi should really be transcendental. Nobody had a proof. And it's quite difficult because if you write down square root of 2 plus square root of 3, you will see that it's almost close to pi. So it's not so clear that you cannot find a more complicated irrational number that is actually equal to pi. And then, many years later, in 1873, Hermite finally showed that E is transcendental. And, these are very strong mathematicians, but you see that these problems have been around for hundreds of years. So just to show how good of a mathematician Hermite is, so most of us are really happy if we have a Wikipedia page. Hermite has a Wikipedia page that just lists things that are named after him. So, he's a very good mathematician. And yet, it took us so much time to figure out that E was transcendental. And Hermite essentially wrote a letter that said he believed that, look, pi will be a much harder thing to prove to be transcendental. But it turns out that only a few years later, Lindemann was able to show that pi is transcendental. In fact, this solved a very long-standing problem posed by the Greeks. That is, if I give you a circle, can you construct a square that has the same area as this circle, only using ruler and compasses? So essentially, this is a problem that was open for thousands of years until Lindemann was able to show pi is transcendental. And I can give you a very quick idea why there is this relation between square root of 2 plus square root of 3 and pi. So imagine that you have a circle of radius 1 whose area is pi. You inscribe an octagon inside the circle whose area, if you work it out, is twice the square root of 2. And if you circumscribe a hexagon outside this circle, its area is twice the square root of 3. And so the area of the circle is somewhere in between, right? So the average should be close to pi. All right, so we have found at least a couple of transcendental numbers. What about the other numbers? So it turns out that Lindemann and Weierstrass came up with a very nice characterization. They said that, look, if x1 to xn are distinct algebraic numbers, then there is no way of writing exponential of x1 to exponential of xn as a linear combination using algebraic numbers. And it turns out that this was actually a very strong hammer, right? It allowed you to show, for example, that E and pi are transcendental. And it also shows you in one shot, it gives you a method in one shot to prove a lot of other numbers to be transcendental. So this was a very strong step forward in this whole area of transcendental number theory. And so essentially their theorem is slightly reformulated, says that if you have distinct algebraic numbers that are linearly independent over Q, so essentially you cannot write them as some a1 times x1 plus a2 times x2 equals 0. Then if you take the exponential function, then there is no non-trivial polynomial relationship between the numbers e to the x1, e to the x2, and so on. And now you see where we are going with this, right? Because now the exponential functions show up. And this was a stumbling block for our original problem. And there's a very long-standing and very comprehensive conjecture in transcendental number theory that essentially generalizes Lindemann-Weierstrass's result that says if x1 to xn are arbitrary complex numbers that are linearly independent over Q, then if you take the numbers x1 to xn and also their exponentials, then at least n of these are algebraically independent. Which just means that there is no accidental polynomial relationship between these n numbers. Now, Shanwell's conjecture is actually a very overarching result. It implies, for example, that pi and e are algebraically independent. Right? There is no polynomial whose roots are pi and e. And in fact, it implies most results that we know today in transcendental number theory. Now, this was a result, in an esoteric branch of number theory, but the way it connects to our problem is that in '96, McIntyre and Wilkie showed that if Shanwell's conjecture is true, this conjecture in number theory is true, then the theory of real arithmetic with addition, multiplication, and the exponential function turns out to be decidable. And this is in fact if and only if. So suddenly now we have connected a very difficult conjecture in number theory to the decidability of a logical theory. And later McIntyre made the claim that, well, if Shanwell's conjecture is true, then the theory of real arithmetic, where you have addition, multiplication, the exponential function, as well as trigonometric functions over bounded domains, is decidable. And this is exactly the theory that we needed. Now, it's quite funny that, McIntyre and Wilkie's proof was really a major breakthrough in our understanding of these decision procedures and their relation to number theory. And McIntyre essentially made this particular claim on this slide in a couple of papers, but the proof was never written down, right? So what McIntyre said is that, yeah, if you look at my proof with Wilkie and you make the obvious changes, or if you make the changes to talk also about trigonometric functions, then this result holds, right? So I think, I believe that this result holds, but it was never written down. The full proof was never written down. So over the last year, we actually at MPI, we ran what we, as kind of seminar to essentially go down, go through these proofs and to be able to write down this McIntyre's claim that if Shanwell's conjecture is true, that then this theory is decidable. And this took us quite a while because, the proof is not simple, but at this point, we can believe this result, right? So we have a full proof that the theory of arithmetic with exponential and trigonometric functions is decidable. And essentially, this brings us back to the place where we started, right? We started with a very simple reachability question that was posed in the context of dynamical systems. And essentially now we have, we can say that if this conjecture from number theory is true, then our problem is decidable. And that's essentially the end of our quest. Well, of course, we don't know if Shanwell's conjecture is true, but this is where we are at this current point. So this is more or less all I wanted to talk about. Let me just end with 3 points. The first point is that, let me call something the programming language's lens, which is essentially the idea that you can take systems, you can mathematically model them, and then you can use logic to reason about the behaviors. So usually we have been very successful in using the PL lens to problems in hardware and software design. But I hope this talk convinces you that the same lens is applicable to systems that are not only software, that go to, for example, continuous time dynamical systems. Of course, in understanding, in applying the PL lens to these new problems, we have to understand new tools and techniques, often from different areas. But this is something that is really worth doing. And the third point I want to make is that science moves really slowly. So if you think about the problems that we talked about, they were posed really thousands of years ago, and we are still sort of making slow progress towards them. So Archimedes knew about pi, but we could prove that pi was irrational only in the 1760s, after we developed the tools of calculus. And we could prove it is transcendental only a little bit more than 100 years ago. So I think in computer science, we have this bad habit of calling things classical papers if they are over 5 years old. But you see, there are many deep problems that require the PL lens that are really hundreds, if not thousands of years old. So I will stop here, and I'll be very happy to take questions. And I'll also be around in the coffee break after this session. Thank you.
Thank you so much, Rupak, for a very interesting talk. And thank you all for the clap emojis. Yes, indeed. Let's thank Rupak. Are there any questions from the audience? Remember, you could either post your questions on Clouder, or you could just raise your hand here and I'll unmute you. You can ask a question. So please do let us know. If any of the other co-hosts can hear me, for some reason, I'm not sure if I can see everything that's happened on Clouder. Could you also double check that there are no questions on Clouder? Okay.
I don't see any question.
Okay, so while we wait for our very shy participants, so I have more of a less of a technical question, but more of a sort of how did you so okay, so I've always find this sort of multi-disciplinary problem solving very interesting, but it's not something I'm personally very good at. Specifically, like the connections that you made between PL and this sort of number theory has really blown my mind. And I feel like unless you really understand both areas very well, it's very difficult to see connections like this. So what is a good strategy to develop the sort of gut feeling for when and how to connect things together?
Well, of course, it's not like you kind of see these problems and immediately see the connections, right?
Mm-hmm.
So essentially, what happened is that, I have worked in the programming languages world for some time, and I have also worked in the cyber physical systems world. And in the cyber physical systems world, these ODEs and these dynamical systems come up as natural objects of study. And then, it's an obvious question to say that, well, just as logic was useful in the other setting, would it also be useful here? Mm-hmm. And then, of course, you talk to colleagues. In fact, one of the people who pointed me to these problems was Ben Worrell, who's actually giving one of the invited talks at POPL this year. Mm-hmm. So, I would look at talks that Ben Worrell or Joel Waknin would give, and I will kind of see the techniques that they were using in their analysis of dynamical systems questions. And then, at some point, there is lockdown, there's, you are at home, you kind of take a textbook and try to see, whether you can read up a little more on the number theoretic aspects. Mm-hmm. And of course, the kind of things that I talked about, these are not really very deep problems in number theory, right? So it's more or less, some number theory 101, if you wish. Mm-hmm. But the main thing is that it's more the conceptual view, right? You see some problems that you recognize could use techniques from a different field, and then you kind of put them together, and then you see how far you can take this. Mm-hmm. So essentially, you have to do some reading, you have to talk with colleagues. Really, there is no magic bullet, right? So. Right.
I think we have another question from Daniel in the audience. I'm trying to unmute you, Daniel.
Yeah, okay. I can unmute that. Okay, so you have linear dynamical systems, I think, with a time bound, and so I think you showed that they were decidable. I mean,
it's decidable modulo this conjecture from number
right.
theory.
Okay, so if you can show it's decidable. So okay, I have two questions. So one thing is like, what benefits does that get you? Because I mean, one thing is like, oh, I mean, sort of like in Turing machines, it's like, oh, it's decidable. I'm sure my Turing machine will solve it sometime, even if that's after the heat death of the universe. Like,
yes, I mean, I see your question, right? So, is there an application? So does it matter to the practitioner? Well, I think there are two answers to your question. One is that it's a very natural theoretical question to understand what we can or cannot do, right? So in that sense, you could say that, look, this is a very basic thing about dynamical systems. We should understand how this works. And of course, the first particular decidability proof may not give you a practical algorithm. In fact, in practice, you would probably just use numerical results anyway. But it may give you an insight into what is happening into these problems. And certainly, if you think about these logical theories, then understanding under what circumstances certain logical theories are decidable is certainly a very valuable exercise, because once you have shown it's decidable, you can show a lot of problems. You can have algorithms for a lot of problems through reductions. And now the first algorithm that you get may not be a very efficient one, but often this has happened that once you have the first idea that something is decidable, later on you can even show its complexity, right? So you can show, for example, that Tarski's decision procedure is only doubly exponential space, right? So essentially, there is this progression of ideas that give you more and more insight into the problem, and proving decidability is one way of getting these insights.
all right. So it's sort of. Are there any? I guess maybe you haven't thought of this, or this is getting into something else. But like, I mean, are there any sorts of tools or like fields or things that are where you'd start to look for these things that would show that you can do it efficiently?
we do not really know how to do these things efficiently,
Yeah.
right? So,
Okay.
yeah.
Yeah. Okay. So my other question is, okay, so you're talking about linear dynamical systems. This might be more of like a what is cyber physical systems, but like what sorts of things can you model with linear dynamical systems with the constraints you mentioned? Like, I mean, I feel like one
Oh,
of
you
the
can
applications.
model a lot of
Oh,
things, right? So
oh,
if you
cool.
go talk to control theorists, so a
Mm-hmm.
major part of control theory is about linear dynamical systems.
Mm-hmm.
And the reason linear dynamical systems are very interesting is because any nonlinear dynamics can be locally approximated very well with linear dynamics. So understanding the behavior of linear systems is really crucial to more or less understanding a lot of physics and a lot of engineering. So, for example, if you think of simple harmonic motion, it's a linear system. Of course, not every possible system is linear, but linear dynamics essentially allows us to design controllers for a very wide variety of actual engineering artifacts, right? So it's a very important class of systems.
So I mean, could you model like some uber complicated, mechanical system like a car or something? Or?
Well, it depends at what approximation, right? So if you just think of, so yeah, I mean, the short answer is yes and no, because if you locally approximate nonlinear dynamics, you will always find linear dynamics that works well in some neighborhood, right?
Okay, so let's thank Rupak again.
All right, thank you. Yep.
For running over time. Thank you so much, Rupak, for a great talk. And remember, Rupak will be here in the coffee break afterwards, after the session, so you can ask him more questions. Thank you, Rupak.
Thanks.